Hi, my name is Nicolle. I'm a PhD student at PUC-Rio, and this work was developed with Shima Parsa and Marcio Carvalho, and it's entitled Foam Formation During Gas Invasion of a Porous Medium Occupied by a Surfactant Solution. So water and gas are commonly injected in the reservoir to maintain the pressure and displace the oil towards production wells. And the amount of oil displaced is both a function of how well the reservoir is swept by the injected fluid and how well the oil is displaced in the pore scale, the residual oil saturation. The enhanced oil recovery methods are the applied techniques to maximize oil production through the interaction between the injected fluid and the rock oil system. Each EOR method acts in one or ideally both of these two factors. Different methods can be used with their own advantages and disadvantages. One of them is the gas flowing. When we have gas flowing in the reservoir, the gas flows to the upper part of the reservoir, leaving a large amount of oil behind. This is called early breakthrough. Also, we have the formation of these instabilities called viscous fingering. So the idea is to reduce the mobility of the displacing phase. We can do that by alternating water and gas. We have better results, but we still have oil remaining. In the third case, the surfactant alternate gas case, first we inject a slug of surfactant solution, then we inject gas. In this case, we have foam formed inside the reservoir. And foams are better injection fluids than the aqueous solutions because they are less sensitive to gravity and permeability heterogeneity. So we have a more uniform sweep front here. Also, the success of foam as an injection fluid highly depends on the foam generation and stability of the lamellae. Foam also provides a solution to the adverse effects of gravity override, early breakthrough, reservoir heterogeneity, and viscous fingering on the efficiency of the gas injection. Foam can behave in different ways inside the porous media. We can have a continuous gas path. We can have bubbles flowing. This is called a bubble train. And we can have gas trapped in bubbles here. The foam has hyperant viscosity by trapping gas in bubbles, reducing the flowing fraction of gas, and providing capillary resistance to the flow. So the idea is to reduce the mobility ratio by reducing the relative permeability of the displacing phase and increasing the viscosity. So the goal is to study foam formation during the drainage process in a 2D porous medium micromodel by visualizing the pore scale displacement. So the idea is to analyze the microscale flow of gas liquid inside porous media and understand that the flow behavior will directly impact the oil recovery method. Also obtain pore scale information that can be used to improve continuous model of foam formation and flow in porous media. To do that, we're going to use a micromodel. It's a 2D micromodel made with glass by Micronet. Here you can see the glass pore structure, two buffer zones, one in the entrance and the other one in the outlet. Here are the sizes of the micromodel, the pore volume, porosity, and permeability, the properties of the micromodel, and the sizes of the channels. The surfactant solution here is a mixture between water and sodium dodecyl sulfate. And the surface tension between the surfactant solution and the gas is 34.4 millinewton per meter when we are above CMC, that is the critical micelle concentration. Here is the experimental setup. We use the syringe pump, a gas-tight syringe filled with air, a pressure transducer to monitor the pressure, the micromodel, an inverted microscope, and a computer to do the image process. So first, we saturate the device with a surfactant solution, and we use different concentrations for different experiments. Then we inject gas at constant volumetric flow rate, 1 milliliter per hour. We measure the pressure and we visualize the flow dynamics. So let's see the micromodel. The gas is being injected from the left to the right, and the device is filled with surfactant solution dyed in red color. So we can see the gas percolating the micromodel. And as gas percolates the micromodel, we have the formation of these thin liquid films here. These thin liquid films. And these thin liquid films, they're called lamella. Lamella are these thin liquid films that separate the gas bubbles. Here is a 3D image of a gas bubble. We can see the lamella, the plateau borders that separate the lamella, and here it's a node that connects the plateau borders. The lamella, they are stabilized by a monolayer of surfactant, and the surfactant has a polar head and a non-polar hydrocarbon tail. Here, this part is in contact with the surfactant solution, and these parts here are in contact with gas. We have different mechanisms for foam formation inside the porous medium. The first mechanism is called leave behind. In this mechanism, we have gas flowing in two adjacent pore bodies saturated with surfactant solution. So when the gas invades the pore body, we have the formation of these two lamellae. Another mechanism is called lamella division. In this mechanism, we have mobilized lamella passing from a pore body to two pore throats that are not occupied by liquid or another lamella. So this mobilized lamella breaks into two new lamellae. You can see here the branching point and the new lamellae. The third mechanism is called snap-off. So in this case, lamellae are created in the gas-filled pore throats. If the local capillary pressure falls about half of the capillary entry pressure of the throat. You can see here that we have an original bubble. This bubble flows through this throat and divides in two new bubbles, this and this one. The last mechanism is called pinch off. You can see here in this yellow area. The pinch off can generate bubbles that are smaller than the pore size. So one bubble pinches another bubble against the post here. And this bubble squeezes the other and forms another lamella. So at the end, we created another lamella. Another important thing here is the liquid fraction. So in the beginning, the device is completely saturated with surfactant solution. And then we inject gas. We keep injecting gas, so we are decreasing the liquid fraction. So in the beginning, we have what we call bubbly liquid or wet foam. And the bubble has this circular shapes here. And during the experiment, we decrease the liquid fraction. So at the end, we have less than 1% of liquid. We call this dry foam. In this case, the foam, they are deformed into this polyhedra shape with curved edges. Here we can see the saturation profile after the experiment. We only have gas and liquid is only present in the form of lamella. At the end, we have this gas percolated path, here digitally colored in red. So, now analyzing the effect of surfactant concentration. In the first case, we are at the CMC, so the concentration is 3.1 grams per liter. And in the second case, this one here, we have 5 times the CMC. So we have higher concentration, but the value of the interfacial tension is the same because we are above CMC. The surface tension is the same, but we have completely different pressure behaviors. You can see here in the curves that for the 1 CMC case, we have the lower value for the maximum pressure compared with the 5 CMC case, that we have higher value for the maximum pressure. Also, the time that takes for the gas to find this percolated path, it's higher for the 5 CMC case. So when we reach this steady state, we're not forming lamellae anymore, and the gas finds a percolated path, so the gas is flowing through the micromodel. Comparing with a case with no surfactant, it's this case here, it takes only 8 minutes for the gas to find a percolated path, because we are forming lamellae that are not stable. And also the maximum pressure, it's 1.8 psi, much lower than the other case. So what we see is that the presence of surfactant completely changes the two-phase behavior in the porous medium. Changing the concentrations, we can see the pressure behavior. When we are below CMC, this case is here, we have lower values for the pressure. And when we are above the CMC, we have higher values for the pressure. So when we increase concentration, we are also increasing the pressure. The pressure increases during the test. And when the gas finds its percolated path, when we are not forming lamellae anymore, we have this pressure drop, and we form these two plateaus here. The first plateau happens when we are below CMC, and the second one when we are above CMC. We don't know yet what is happening here, but to understand the dynamics of the whole process, we started visualizing the flow in a region of the micromodel. So this yellow square here shows the area that we are analyzing now. So we have a video, and we can see the gas flowing, the foam formation mechanisms. We can quantify the lamellae and its velocities. To do that, we have to use image processing tool. And we use, the first input is an image of the device saturated with air. We call this matrix. We need to use the binary image, the black and white. The second input is the device filled with lamellae. We do the same thing. We're going to use the binary image. Then we subtract this image from this one, and we can identify the lamellae. After this identification, we can quantify, we can calculate its velocities and its properties. So, counting the number of lamellae with time. Here we can see the number of lamellae per millimeter square. And we can see that for higher concentrations, we also have a higher number of lamellae. So when we increase the concentration, we are increasing the lamellae formation. But at the end, when we stabilize, when we reach the steady state condition, we have almost the same values for all cases. Comparing related with the CMC, when we are half CMC, add the CMC 2 and 5 times the CMC, we can see that the maximum number of lamellae, they increase with concentration. Now we are working to track the lamellae, so we are using another ImageJ processing tool. And at this step, we are using a video, and we can see the lamellae flowing. We can track its properties. We can know all the velocities, the positions. We can have data like this one. Here we are seeing that we are tracking the lamellae, and what we are showing here is the mean velocity of the track. So in these areas here where we have blue, you can see that this is an area that the lamellae is not flowing. The gas here is trapped. But on the other hand, in these areas, these yellow areas here, these paths, we have a bubble train, we have the gas flowing. This is the preferential path flowing at high velocities. And now we are working to do this identification and these quantifications. And my conclusions are that the gas foam films, they are formed. and create resistance against the gas flow, increasing the magnitude of viscous forces against capillary forces. The pressure behavior do not depend only on the surface tension. The surfactant concentration changes the population of lamellae that compose the foam, impeding the free motion of gas through the porous media. We are obtaining detailed information on the dynamics of lamellae formation and speed that can be related to the macroscopic flow behavior. I would like to thank all the funding agencies and thank you for watching.